Hey Chemistry, we're going to talk through ions and how you can figure out what charge ions form from valence electrons. The power of being able to do this from the periodic table is that you don't have to memorize 118 different charges for 118 different elements. You can simply use the periodic table and as a tool and figure out the charge for probably more than half of those elements. It just saves you a lot of work, a lot of mind space, a lot of trouble if you can use the periodic table to help you figure out ion charges. Okay, so we're going to talk through how to do this. First of all, in order to be able to use the periodic table to figure out the charge of ions, you have to be able to tell me how many valence electrons that element has. Okay, so you can do this a couple different ways. You can do this using the Bohr model. For example, if we're going to talk about, let's do nitrogen. You can draw the Bohr model for nitrogen. We know nitrogen has 7 protons. We know it has 7 electrons. 2 electrons fit into the first energy level, and then the remaining 5 electrons get put into the second energy level. So the outermost energy level has 5 electrons, and we call those electrons in the outermost valence shell, we call them valence electrons. So that is one way to figure out the number of valence electrons that an atom has. Another way is by looking at the electron configuration. If we draw the electron configuration for nitrogen, we have 1s2, 2s2, 2p3. We look at all the electrons in the outermost energy level. So notice we have 2 energy levels here. We have energy level 1 and energy level 2. And so if we count up all the electrons in that outermost energy level, there are 5 electrons in the outermost energy level, or 5 valence electrons. That's another way to figure out how many valence electrons an atom has. Now, there is a third way to figure out how many valence electrons an atom has, and that is when you look at the families on the periodic table. We have shown before that the families on the periodic table all have consistent outer shells. I'm going to do this for the first family just because it's the least amount of electrons. So hydrogen would look like that. Lithium looks like that. Sodium is getting a little bigger. Looks like that. Okay, and within the first 3, you see the same number of valence electrons. Hydrogen has 1 valence electron. Lithium has 1 valence electron. Sodium has 1 valence electron. And if we kept drawing out the Bohr models for all of the elements in that first alkali metals family, we would see they all have 1 valence electron. And this is true for every single family in the representative elements. So the first family, the alkali metals, have 1 valence electron. The alkaline earth metals have 2 valence electron. If you draw out just beryllium, you can see that. Beryllium has 2 valence electrons, and everything underneath beryllium in that family has 2 valence electrons. Boron has 3. Again, if we want to verify this, we can draw out the Bohr model for boron and see that it's 5 electrons get distributed, 2 in the first shell and then 3 in that outer shell. Carbon's family has 4 valence electrons. Nitrogen, we just did, it has 5. The oxygen family, they all have 6 valence electrons. The halogens have 7, and the noble gases have 8. And again, if you want to go through and verify that, you can do that by writing out the Bohr model, which we have done. You have a chart with the first 3 or 4 rows with their Bohr models written out, their Lewis dot diagrams written out. If you draw the Lewis dot diagram for all of these elements, you can see the number of valence electrons also and see that it's consistent in a family. You can also do this by drawing out the electron configurations. And so this is the third way to figure out how many valence electrons an atom has, is by looking at the family that it's in. If it's a representative element, then its family number, if you're looking at the 1A's, 2A's, 3A's, and so on, its family number in terms of A's is how many valence electrons it has. So we have 3 different ways to figure out the valence electrons for an atom. If I were to ask you just a random representative element, you should be able to tell me how many valence electrons that element has. Now that we know how many valence electrons atoms have, I'm going to write it on top of the families again. We can use this information to figure out the charge of the ion. So we see that special stability occurs in the noble gases, and that special stability occurs for the noble gases because their outermost energy levels are full. Their S and P shells are always full. And that gives the noble gases this special stability. And ions are going to form to match the stability of the noble gases. So ions are either going to gain electrons until they have 8. We call that an octet. In this case, if they gain electrons in order to get 8 electrons in that outermost shell, they are going to be a negative ion, and negative ions we call anions. If ions lose electrons, they can also gain that noble gas stability by losing electrons. So if they lose electrons until their outermost electron shell is empty, then they're going to be a positive ion, and positive ions we call cations. Okay, so just a minute here on pronunciation. I know that if you were looking at this, you may pronounce those words differently, but they are in fact pronounced anions, anions, and cations. Cations. So a negative ion is an anion, a positive ion is a cation. Okay, so let's look at this in practice. Let's look at some of these smaller atoms, and for the sake of time, I'm going to draw their Lewis dot structures. So let's do this first row in terms of Lewis dot structures. Again, you already have this done. If you go pull out that chart where we drew Bohr models and Lewis dot diagrams for those first couple rows, you actually have this done. So I'll do it quickly here, and you can go find that chart so you don't have to do it again. All right, so here is my entire second period written out in terms of Lewis dot diagrams. Remember, in Lewis dot diagrams, we only write out their valence electrons, which becomes very useful. Okay, so they're all going to either gain electrons until they get 8, just like the noble gas family has 8. We call that an octet. Or in the case of helium, who has a full energy shell with 2 electrons, we would call that a duet. So hydrogen and helium are going to fill in that first energy level, that 1s orbital, with a duet of electrons. Everybody else on the periodic table wants to fill their s and p shells or empty their s and p shells so that they have an octet. Okay, now which way are they going to go? Well, that depends on what they're closer to. So if it takes less electrons to fill than to empty, then they're going to fill, and vice versa. So let's look across this periodic table. All right, so lithium has 1 valence electron. Is lithium more likely to gain 7 to get to 8 or lose 1? It's closer to losing 1, so lithium's going to lose that 1 electron. Now, anytime you lose something that's negative, you become positive. So lithium is going to become a positive 1. It lost 1 electron. It's a positive 1. Beryllium, will it gain 6 to get to 8, or will it lose 2? It's closer to losing 2. So beryllium's going to lose its 2 valence electrons. Beryllium has lost negative electrons. It is now positive, and it's lost 2 electrons, so it's now a positive 2. All right, so I want you to pause this video and you do boron. What charge is boron probably going to form? So boron's either going to gain 5 or lose 3. So it's going to lose its 3 to become boron 3 plus. We're going to skip carbon for just a second. Let's start on the other end. Let's look at fluorine. Okay, fluorine has 7 valence electrons. So is it going to gain 1 or lose 7? It's going to gain 1. So fluorine is going to gain something negative. It's going to gain a negative electron, so it's going to become negative, and it's gained 1. So it's going to be a fluorine negative. How about oxygen? Oxygen has 6. Is it going to gain 2 or lose 6? It's going to gain 2. So oxygen gained 2 electrons. It's gained negative electrons. It's going to become negative. So oxygen is going to be an O2 minus, and oxygen's gained 2, so it'll be a 2 minus. Fluorine, nitrogen. Is it nitrogen going to gain 3 or lose 5? Why don't you pause here and tell me what charge nitrogen's going to form as an ion? Nitrogen's closer. It's easier to gain 3 than it is to lose 5, so it's going to gain 3. So nitrogen is going to be a 3 minus. Okay, now carbon is interesting because carbon has 4, so it could either gain 4 to get 8 or lose 4 to be empty. So carbon's family is kind of in an interesting predicament, and what we see with the carbon family is they go with their group. So nonmetals are going to do what other nonmetals do. They're going to gain electrons and become negative. Metals are going to do what other metals do. So metals are going to lose electrons and become positive. So carbon usually doesn't form ions, but if it does, it's going to form a 4 negative ion. Silicon and germanium don't really form ions either. They're metalloids. Tin, lead, and Fl at the bottom, those 3 are metals. And so they're going to do what metals do, and they're going to gain electrons and become a 4 positive. So this family kind of does both. It can either go for negative, which is what the nonmetals are going to do, or it can go for positive, which is what the metals are going to do. Okay, so at this point in time, you know what every family is going to do. We've given you one example from every family, so I should be able to pick out any element from the periodic table, any representative element, because we haven't talked about the transition elements yet, any representative element, and you should be able to tell me what charge it's going to form. Like strontium, what ion is strontium going to form? And how about iodine? What ion is iodine going to form? Now notice all the noble gases already have 8 or a full energy level, 2 in the case of helium. So they don't form ions. They don't lose, they don't gain. They're always neutral. They're unreactive. All right. So this is how we figure out ions from valence electrons. We'll do practice with that in class. And I just want to recap a couple things about ions before we move on so that we know everyone's on the same page. So one of these things is patterns. Well, one of these patterns that we see with ions is the type of element. So we just talked about this on the last slide, but when you look at the type of element, so here's the metals, right? And then here are all the nonmetals, and it keeps going down. Those groups form very consistent elements. All the metals do what? Do they gain electrons or do they lose electrons? All the metals are going to lose electrons and form cations. Now, the periodic trends help us explain this. Think of their ionization energy. Ionization energy for metals, they're all the way on this left side, tend to be much lower than ionization energy for elements all the way on the right side. Similarly, elements on the bottom tend to have lower ionization energies than elements on the top. And so metals tend to fill this left bottom part of the periodic table. They tend to have really low ionization energies. They give up their electrons really easily. It doesn't take very much energy to remove their electrons. And so it makes sense that they would form cations. Nonmetals, on the other hand, tend to be on the right top part of the periodic table. They're going to tend to have really high ionization energies, very high electronegativities, high ionization energies. It takes a lot of energy to remove that electron from them. They have high electronegativities. They have a high tendency to attract electrons to themselves. And so it makes sense that the nonmetals would gain electrons and form anions, which is what they do. Most metals form positive ions. Most nonmetals form negative ions. We see this definite pattern within the types of elements on the periodic table. Same with families. We talked about how families have very consistent valence electrons. That means they have very consistent ion charges that they form also. So we could go ahead and label the tops of the families with the types of ions they form. Like the alkali metals are going to form a 1+. Alkaline earth will be a 2+. The boron family will all form 3+. The carbons, we talked about how they can go either way. How about nitrogen, oxygen, and fluorine? Take a minute and tell me what ion charges these families are going to form. Okay, nitrogen should be a 3-, oxygen's a 2-. The halogen family, they're all going to form 1-, and then noble gases don't form ions. So anything inside the family, very consistent, they all form that same charge. Okay, so on this, I just want to define cations and anions very carefully. If you don't have a written definition for anions and cations, write it now, please. Cations are going to be positive ions, which means that they have lost electrons. Anions are going to be negative ions, which means they have gained electrons. So those are vocab words you should be able to use going back and forth. And again, we can figure these out. We don't have to memorize these. We can figure these out based on the valence electrons that occur and whether those valence electrons are more likely to gain or lose electrons to get that full octet. Okay, the last thing I want to talk about is electron configurations for ions. So when we're talking about electron configurations, what we're doing is we're taking the electrons that exist in the atom and we're describing exactly where those electrons are localized around the atom, right? Well, we can do this for ions also. If we go back to our periodic table here, and we pick something like fluorine, let's look at the electron configuration for fluorine. 1s2, 2s2, 2p5. Now, fluorine we know has those 7 valence electrons. It's going to gain 1 electron and become an F minus, right? So since it has gained 1 electron, you need to put 1 more electron in the electron configuration. So the electron configuration for F minus would just have 1 additional electron in it. 1s2, 2s2, and then instead of being 2p5, it's going to be 2p6. And notice we talked about how electrons gain or ions gain or lose electrons in order to match the stability of the noble gas. Well, look at the electron configuration for fluorine. It matches the electron configuration for that noble gas that it is closest to. It's exactly the same. We see this on the other side too. If we look at sodium, for example, the neutral atom of sodium would have an electron configuration of 1s2, 2s2, 2p6, 3s1. Now, sodium is really close to having that second energy level completely filled as long as it can get rid of its third energy level, right? So sodium has 11 electrons. It's going to lose 1 electron to form Na+. So why don't you pause the video here and write out the electron configuration for the sodium ion. It's just going to have 1 less, 1s2, 2s2, 2p6, and that 3s1 electron just gets dropped. Notice it matches the electron configuration for neon, just like fluorine matches the electron configuration for neon. There's a term for this. We call them isoelectric. Iso means the same, and electric is talking about the electronic structure. So ions are isoelectric with noble gases. There's your vocab word for the day, isoelectric. Now, there is a way to name ions as well. Instead of calling it the Na plus ion or the F minus ion, there's usually we use names to indicate that it's an ion. So for positive ions like Na plus, the name is just the element name plus the word ion. So for positive ions, it's super easy. So this is literally called the sodium ion. Na plus is called the sodium ion. What would Mg2 plus be called? Anions are a little bit trickier. In order to name a negative ion, we're going to have the element name, but we're actually going to take off part of the element name and put on IDE, "ide," before we tack on the word ion. So fluorine, the element fluorine, we're going to take off its ending and put on the ending "ide," becomes the fluoride ion. So oxygen would become oxide. Nitrogen would become the nitride ion. What would chlorine become? Okay, so that's as far as we're going to go with ions today. That's a lot of information about ions. Let's think about this. Let's process this. Let's come back together and practice this. Let me know what questions you have. I will see you in class.